We started the chapter looking at exponential growth and decay, and we're going to come back to it the last section to look at this similar type problems, but a little bit different, and we're going to use some of the stuff we learned about logs to solve them. Back in that first section, we talked about certain assets like homes can appreciate or increase in value over time, and then other assets like cars depreciate or decrease in value with time. This first example looks at one of those. Suppose you buy a car for $22,000 and the value of the car decreases by 16% each year. Write an exponential function in the form y equals a times b to the x power, the same type of general exponential equation we had before. That could be used to model the price y of the car. Write a function in terms of x, the number of years since you purchased the car. All right, so we've done some problems like this earlier in the chapter. We want to figure out first, what is our A going to be here? What is our initial value? And our initial value of the car is $22,000. Okay. B is our multiplier, and we do know our multiplier here. It's telling us that the price of the car is decreasing 16% each year. If the car is currently at 100% and it's decreasing 16%, what is the value of the car going to be every year? 84% of what it was the year before. So what we want to do in this problem, since it's a decreasing one, is decrease and subtract that 16% from 100%. Or another way of thinking about it, if we change to decimals, we would be subtracting our percentage from 1. So if we change 16% to a decimal, it would be 1 minus 0.16. Okay, that will then tell us what the value of the car is each year. The x would be our multiplier each year, x. If you simplify that a little bit, that would be the same as the equation y equals 22,000 times 0.84 to the x power. So that's our general equation that we could use then to find how much the car is at any year. For example, down here they ask find the value of the car 2 years later, 3 years later, 7 years later. It's easy to calculate out now using this formula. All we have to do is plug it in. So if we want to know what is it 2 years later, all we got to do is plug in 2 for our exponent, and then it's kind of a calculator problem. You just got to plug it in. So if we put this information into the calculator, we have 22,000.84 to the power of 2. And if we enter it, we get the value of the car to be about $15,523. And again, you could easily do the same thing for 3 years if you want to do 3 years. Same equation. The only thing that changes is our exponent of 3, or if you want to find it at 7 years, then you would put the exponent of 7. So once you have this general equation, it's really easy and quick to get the value. And then it's just simplifying it out again using calculator. You'd find this one to be $13,039.49. If you want it 7 years later, do the same thing, enter it. It gets all the way down to $6,491.99. So you can see the value of the car is decreasing exponentially. All right. So what does that tell us? Anytime you are doing a problem where it's exponential decay, where it's decreasing or depreciating in value, you want to use this kind of modified equation right here of our y equals ab to the x. Your multiplier is going to be 1 minus whatever your rate is, where r is a percentage. So this b just becomes 1 minus whatever the percentage decrease is. So anytime they give it to you as a percentage, decrease it from 1 or subtract it from 1, which is really like 100%. Let's try an example problem here. Another one. This one says a cup of coffee contains 130 milligrams of caffeine. If caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for half of this caffeine to be eliminated? Okay, well, we want to go through and try to enter all this information into that same equation we just had. So we start with 130, that's our initial value. It's decreasing by 11%, so this would be 1 minus 0.11. And that would then tell us how long in hours. So we got this equation. If you subtract 0.11 from 1, that would be 0.89. So that would be our multiplier in this problem. All right, so now let's answer the question. It says, how long will it take for half of this caffeine to be eliminated? Now, we don't know a time in this one, so we don't know anything we can put in for x, but we do know how much we want at the end. They said, how long until half of the caffeine? Well, if we started with 130, half of 130 would leave us with 65 as our ending value. So what we have to do is solve this equation for x. So we want to get and see how much time that's going to be. Well, if we want to solve this equation, we want to try to get x by itself. If we're going to get x by itself, we first need to get this exponential part by itself, which means getting 130 out of this problem, or out of the right side of the equation. Since it's being multiplied to this exponential, we'd want to divide by 130. Dividing by 130, it leaves us with 0.5, or 1/2 on that side. And that makes sense because we're trying to find out how long till there's half of it left. All right, now we get into this part of the problem. We want to eliminate and try to get that x by itself. And this is where that stuff we kind of talked about with logs comes in. We can't solve this unless we introduce logarithms into the problem. So what we want to do is take the log of both sides. And it's up to you whether you want to choose regular log or natural log in order to do this problem. I'm going to use natural log. So what we're going to do is write in the log of both sides. So we're going to do the ln natural log of 0.5. And on the other side, we're also going to do ln. Okay, so whatever you do to one side, you got to do to the other. Now what that allows us to do using the power property of logs is take this exponent and move it down as multiplication. So our problem now turns into ln of 0.5 equals x times ln of 0.89. All right. We want to get x by itself, so our last step to get x alone is to divide by ln of 0.89, both sides. That cancels out, and now we can figure out what x is. So now it becomes a calculator problem. So on your calculator, you want to take the natural log of 0.5, make sure you close the parentheses, divided by natural log of 0.89. And if you hit enter, it'll tell you approximately the time it's going to take. It looks as if it takes about 5.95 hours. So that's how much time it would take your body to eliminate the caffeine. All right, for tomorrow, I want you to try number 2. See if you can do that one. It's a similar type problem, exponential decay problem. Try number 2 out, see what you get. What we're going to do is go down and look at a different type of problem with exponential growth. Exponential growth is where your quantity is increasing by a fixed percent each year. So very similar equation again. This is again based off our general equation, a times b to the x. Your multiplier, if you're increasing by a percentage, you'd want to add it to 100%, or if it's a decimal, add it to 1. So anytime you're increasing by a percentage, you need to add it to 1 to find your multiplier. Let's read through this one. It says in 1990, the population of a city was 120,000. Since then, the population hasn't increased 1.5% each year. If the population continues to grow at this rate, what will be the population in 2010? All right. Well, we want to find our starting value. That would be 120,000. Okay, what is our multiplier going to be? It's a percentage increase, so we need to add it to 1, and it would be this percentage. We need to change 1.5% to a decimal. That would be 0. We got to divide by 100, 0.015. The general equation is just going to have x and y. If we simplify, be 120,000 times 1.015 to the x. All right, if we read on, they want us to know what's the population in 2010. Our starting year was 1910. Our ending year is 2010. That's a difference of 100 years. So if we're going to solve this one, our exponent's going to be 100. Again, this becomes calculator problem now. You want to enter it in your calculator and see what you get. So let's try it out. We got 120,000, 1.015 to the power of 100. And that'll give us our new population. So it looks as if the population now of the city is 531,845 people. So that's an example of exponential growth. We're growing as the population goes. Now again, you can solve these problems too if you solve backwards and they give you different information. Let's look at number 4. Number 4 says the population of a city of 1 million is increasing at a rate of 3% each year. If the population continues to grow at this rate, how many years will it take the population to double? All right, so on this problem, we have our initial value is 1 million. Our rate increase is 3%, so we have 1 plus 3% as a decimal is 0.03. How many years? We don't know what x is, but we want to know how long till the population doubles. If it's doubling from 1 million, that would end up at 2 million. So this is one of those we're going to have to solve kind of backwards again. Start out by dividing. We want to get our exponential by itself. Divide by 1 million. Cancels out here. 2 million divided by 1 million is 2 because it's doubling. 2 means it's doubling. All right, how do we solve this one now? If you have a variable in the exponent, you need to use logs. And you can use natural log or common log. Let's use common log this time. Let's log both sides. Okay, what that lets us do is bring down our exponent. So what we have is log of 2 equals x times log of 1.03. If we divide now by log of 1.03, we get x by itself. So calculating out the answer on our calculator, this time we're using common log. And again, it doesn't matter. Log of 2 divided by log 1.03. And it looks like the answer is about 23.4 years. I guess our time here is x equals 23.4 years. All right, we'll look at some more of these in class tomorrow.